Floating wind farms represent a revolutionary branch of offshore renewable energy technology. Unlike traditional offshore wind turbines which rely on fixed foundations anchored to the seabed, floating wind turbines are mounted on buoyant platforms that remain tethered to the ocean floor via mooring systems. This design innovation provides the ability to deploy wind energy systems in water depths exceeding 60 meters, thereby unlocking vast stretches of the ocean where the wind resource is abundant and strong. With the potential to capture higher capacity factors due to more consistent offshore winds, floating wind farms can significantly advance the contribution of wind power to the global energy mix. The primary purpose of floating wind farms is to exploit the untapped wind energy resources found in deep water locations that are inaccessible for conventional fixed-bottom turbines. In regions where shallow coastal waters are scarce or where the seabed conditions are unsuitable, floating platforms offer a practical and efficient solution. Key components of these systems include the floating structure or platform, the wind turbine comprising rotor blades, nacelle, gearbox, and generator, robust mooring lines that secure the entire assembly, and subsea power cables that transmit the harvested electricity to onshore grids. Together, these elements are engineered to work in unison, ensuring that the turbines remain stable and operational amid the dynamic forces of the marine environment. At the heart of floating wind farm operation is a familiar principle: converting wind energy into electrical energy. When wind flows past the turbine, its rotor blades capture the kinetic energy and convert it into mechanical energy, which is further transformed into electrical energy by the generator. However, the floating nature introduces additional complexity to this process. Advanced control systems are employed to stabilize the turbine's orientation, compensating for the platform's movements due to waves, currents, and wind gusts. Meanwhile, sophisticated mooring systems manage the tension and dynamic loads imposed on the platform, ensuring that the turbine remains correctly aligned to maximize energy capture even in tumultuous sea states. Floating wind farms offer several notable advantages over their fixed-bottom counterparts. Their ability to be sited in deeper waters expands the geographic potential for wind energy generation to include numerous coastal areas previously constrained by shallow water limitations. This access to stronger, more consistent winds often results in higher energy yields and improved operational efficiency. Moreover, the remote offshore location of these installations minimizes visual intrusion on coastal landscapes and reduces conflicts with other maritime activities such as shipping and fishing. In addition, the installation of floating platforms can present less disturbance to the seabed, an environmental benefit that enhances the overall sustainability profile of these projects. Despite these benefits, considerable challenges remain on the road to commercial scalability. Engineering floating platforms that are both structurally robust and economical is no small feat. They must endure the relentless forces of nature, including high winds, turbulent waves, and corrosive saltwater. The design and maintenance of mooring systems that secure these turbines also impose significant technical complexities, as even minor failures can compromise the entire installation. Additionally, integrating the power generated from remote deepwater sites into onshore electrical grids demands advanced and reliable subsea cabling and conversion technologies. These technical and financial hurdles are critical areas of ongoing research and development in the industry. There are several design concepts for floating wind farms, each tailored to meet specific environmental conditions and technical requirements. The most common types include spar buoy platforms, characterized by long, cylindrical structures with heavy ballast at the bottom. These platforms achieve stability through deep submergence. Semi-submersible platforms, featuring multiple buoyant columns interconnected with a supporting framework. These designs offer adaptive stability in a range of sea states. Tension leg platforms (TLPs) are secured by vertically tensioned mooring lines that restrict vertical motion, ensuring steadiness even in rough seas. Each design has its own balance of stability, ease of installation, and cost-effectiveness, and the choice among them is often dictated by local oceanographic conditions and project-specific requirements. Floating wind farms are strategically deployed in regions where deep waters and reliable wind resources converge. Coastal areas such as those off Japan, Norway, Scotland, and the United States West Coast present ideal conditions for these installations. The vast offshore areas in these regions, combined with regulatory support for renewable projects and the need for sustainable energy solutions, make them prime candidates for floating wind farm development. This geographical flexibility increases the potential reach of wind energy, making it an increasingly attractive option for many nations looking to diversify their energy portfolios. A prominent real-world example is the Hywind Tampen project off the coast of Norway. This ambitious venture, consisting of 11 floating wind turbines, has been engineered to operate in some of the most challenging sea conditions. Positioned approximately 140 kilometers from shore, Hywind Tampen not only powers oil and gas platforms with renewable energy but also demonstrates the operational viability and scalability of the technology. Its success has provided valuable insights into the performance and reliability of floating wind systems, serving as a benchmark for future commercial projects. Looking ahead, the next challenge on the path to commercial-scale floating wind farms revolves around reducing the overall costs and improving the resilience of the technology. Achieving economies of scale through mass production and leveraging advancements in materials, manufacturing, and control systems are essential steps forward. There is also a need for further optimization of mooring designs, platform topologies, and grid integration solutions to lower the levelized cost of energy LCOE for floating systems. With increased investment, stronger regulatory support, and continued technological innovation, the industry is poised to transition from pioneering prototypes to full-scale, commercially viable installations, ushering in a new era for offshore wind energy. Floating wind farms thus embody a forward-looking solution that merges engineering ingenuity with the urgent need for sustainable energy. As research continues and costs decrease, this technology is poised to play a pivotal role in the global renewable energy landscape. For anyone intrigued by the future of offshore wind or by the complex interplay of environmental, economic, and technological factors shaping our energy future, floating wind farms are proving to be one of the most innovative and promising avenues. There remains much to explore in this field, including emerging trends in hybrid systems, advanced energy storage integration, and the implications of large-scale deployment on marine ecosystems.